Okay, so thank you very much for coming to the talk. I'm happy that there is this nice audience. The title is a bit different because I decided to put basically the title of the paper rather than the title that I gave at the beginning. And so we're happy because we have this Infocom paper accepted with Bruno Benat and Antoine Vandeville. So with Bruno Benat, we had a very tight collaboration, and we did this work as a binom, more or less. And basically, we worked together with a stagiaire, so Antoine Vandeville, to help us out with some simulations. And this is why I want to say this, that I was very happy about this collaboration. It was one of the best collaborations I have had in writing a paper. So let's put the problem. So the problem has a context, which is we study generic online social platforms. I will explain what generic means. Anyway, we study online social platforms. And it is very important to say that I use the word platform instead of the word network. So, because in this talk, I will be very much interested in looking at the structure of the platform itself, rather than just the graph, just the social graph. And my aim is to rank users based on their influence on the platform. So I will explain more how we will do that, but let us first talk about user ranking. So user ranking is a very important subject nowadays, especially in many companies are interested in identifying highly influential users. Some are like the big influencers, some others are like some medium influencers or some local influencers. And the aim is especially advertisement. Or another aim could be, for example, to promote some political ideas. For example, I want to promote the idea to vote for this candidate, for example, or to say that this candidate is not good. So this second thing that I said goes mostly into fake news, and nowadays there are many bots that are employed to spread this false information and essentially influence in a bad way the social network, the users. And these bots actually find themselves in a platform. So this is why it's important to analyze and understand the platform itself. So let's first of all see what is a social network. So usually this is a static graph, a social graph. And in this graph there is a constant number of users. We call this graph here leader graph because we draw a line, we draw an edge from an I to a J, when I is the leader of J. And for each user there is a list of followers, F of I, and a list of leaders, L of I. So in this example here, if you take node 1, basically the followers of 1 are 2, 3, and 4 because there is an arrow that starts from 1 and goes to these other 3 users, whereas only 3 is the leader of 1. So if we take node 5, we have that the followers of 5 are 4 and 6, and the leaders of 5 are 3 and 6. This is just an example of a static graph. So who's the influencer? This is the big question that everyone wants to answer. So there are many centrality measures for these static graphs. And for example, one of the most simple ones is the degree. So the degree of a node, the degree of a node can be like a measure of centrality, because if there is a large in degree, so there are a lot of users that have reference to this node, but when there is a large out degree, so this node can spread its influence to many users, at least on a single hop. In this example, the max in degree is 4, user 4, and the max out degree is users 1 and 3. But since degree is a bit of a simpler measure, there is also like closeness centrality and bitness centrality. Both of these actually use the shortest paths. And the shortest centrality is defined as the inverse of the sum of shortest paths from the node to any other node in the network. And if we take this, multiplied by n. So if we take like this definition, the max is again user 3. And there's also bitness centrality, which is a bit more interesting because basically it characterizes the importance of a node in transferring the information. So you basically count how many shortest paths will pass from this node, from node I, and for all source destination pairs. So this is why we take the sum of all source destination pairs, and sigma st of I is the number of shortest paths that path from node I. So this is how so things are for this. So all these definitions use the shortest path, but this is not necessary to have shortest paths, right? So because information can be disseminated from other paths as well. Sometimes maybe I want to send a message, for example, to Jim, but sometimes this message can pass from many other users and arrive to Jim from some other path, which is much longer. So potential information can be diffused in the network from many paths, okay? So there are spectral centrality measures, and these will use basically an adjacency graph, an adjacency matrix. We call here the leader graph because for every row, we put once the followers, right? So we have the eigenvector centrality, which is basically we find it by finding the eigenvector of the spectral radius, and basically the maximum entry of this eigenvector will be the most influential user. And there is also cut centrality, and this cut centrality basically gives less importance to longer paths. So there is this weight A that multiplies the leader graph L, which is less than 1. So basically the more you go far away from the node, the less important it is.
Do we have any kind of empirical evidence regarding the importance, the relevance of these centrality measures?
Well, to be very honest, possibly there are many papers, but I cannot cite right now one paper. There is this book of Newman, who has extensively studied these centrality measures, and he gives in this book many examples. But I cannot tell you right now from the heart.
Different notions of centrality are relevant to different types of networks?
I guess, exactly.
But the citation network has different kind of...
centrality than something else, yeah.
That's what I'm saying.
Yeah, exactly. I think that different centrality measures will be applied to different, propagation to different... so the question is basically for us is, are these centrality measures good enough to find the influencer, for example, in a social platform? So this is the question. And essentially, the answer is no, because such models do not capture neither the user activity nor the structure or the algorithms that are running on the social platform, and neither the competition among users. So they don't capture anything, because, for example, you might have a node that is very central for any centrality measure, but at the end of the day, this node does not post anything. It doesn't have any influence to the network, right? So imagine I have many friends and I never post anything, so I don't have any contribution. So all these aspects that I said here play a very crucial role for post-propagation and influence, but so that centrality measures make no sense, basically, if you don't include these. So let's see, first of all, what activity means, right? So this is not a real graph. It's just like an example. And it shows basically 5 nodes. And there's a central node, a specific node 1 that pushes with rate lambda 1 some posts in the platform. And there is 2 and 3 who are pulling this information with rate M2 and M3. And they are also pushing themselves some information, lambda 2 and lambda 3, in the platform. And finally, there are these users 4 and 5 who are pulling information from 2. So if all the rates of push and pull are positive, then 4 essentially should see posts from both 1 and 2, right? Because since he's pulling information from 2, let's say, and since 2 is pulling information from 1, and since both of them are pushing information in the network, then posts of both users should arrive at 4. But if, for example, user 2 stops pushing himself information, there will be only posts from user 1 that arrive at 4. Similarly, if node 2 stops pulling information from 1, right, he will only push his own information, and the information that 1 is posting will never reach 4. So in this sense, I say that there is the activity of push and the activity of pull, and either of which, if we set them to 0, they will influence a lot what is the final post that the user will see, right? Okay, another thing is the structure of the social platform, which is basically what is appearing and what is the platform allowing us to see, right? So basically in Facebook or in Twitter, like when you open like your account, you have this newsfeed, and you have, I'm user 1 and I'm looking at this newsfeed, but what is presented actually on the newsfeed depends on the curation algorithm of Facebook. Because Facebook might want me to see specific like postings, or maybe they want to promote posts that are more they have a bigger number of likes or of comments, etc. And so what I see in the order I see depends a lot of what the platform is placing there. Another thing is what I am doing, because basically I am pulling content, so I will pull content based on how I see things, first, second, third, etc., and on which is my content. So, as I said, so what is actually presented in the newsfeed? How is this ordered? Is it time-stamped, or is it the most popular content? How does the platform curation influence competition among posts? Because maybe there are 2 users that are friends of mine. I should be able to see posts from both, but for some reason, let's say Facebook shuts off completely one user for some reasons that we don't know, and finally, we don't have the access to his postings, okay? And then there are my private decisions. What do I pull? So, for example, in this example, if the platform does not show to user 4 on his newsfeed content from user 1, then such content will never reach 4, right? Okay, so these are just some examples. So we want to propose a new model and a new metric that will combine the graph structure and will combine the pull and push activity as well as the platform structure and user decision. So it's a really ambitious thing, but let's see how we can do it. So this is what we are going to do. We are going to take each node, and in each node, we are going to model this node by a newsfeed and a wall, exactly as Facebook and Twitter work, right? So there is a rate of posting on the wall, and there is a rate of reposting from the newsfeed to the wall. So we call this lambda n, is the rate of posting, and mu n, the rate of reposting. So all the other users have also a wall and a newsfeed, and they are posting and reposting themselves. So suppose that we have a number of users n that form a directed social graph, exactly as it was in the static case. And each user has a set of followers and a set of leaders. So the 2 lists, the wall and the newsfeed in our example, have a size k and a size m that are predefined. But we will see that they will not play a major role. And basically, these sizes are, let's say, the importance of that the last k posts are important for me to read, or the last m posts are important to be disseminated, because the others are very old, for example. And now, the rate of arrival on the wall of user n will be the addition of lambda n plus mu n. And we consider them to be positive strictly for everyone. So at least one of the 2 should have a positive rate, okay? Now, the content, this is an assumption that we do in this model, that the content posted in a user's wall will instantaneously appear on the news feeds of these followers. So as soon as I put something on my wall, this is pushed, let's say, on the news feeds of all my followers. So this is actually how the social platforms are working, right? Now, the rate of post arrival on newsfeed n, based on this assumption, will be the sum of all of his leaders of the lambdas and the mus. Because if each leader is posting something with rate lambda or reposting on his wall with rate mu, by my assumption, this will appear directly on my newsfeed. So the sum of all the leaders will make this. Okay.
Does the posting rate, the posting on a wall rate, does that not depend on where the information is coming from initially? Is it the same for every other wall?
So I have a posting rate that is the posting rate that I am deciding to write on my own wall, which is lambda.
But Is that applying equally to everything in your newsfeed? Is it just the same probability that you're going?
Oh, I didn't say anything about probabilities. I just said that there is an arrival of posts. So I'm posting, for example, 5 posts a week on my wall. And I'm going to the newsfeed, and I'm taking from the newsfeed 2 newsfeeds, and I'm retweeting them or resharing them. So this will be up. So it's just a rate of activity, basically. Now, based on this, so any post generated by user n takes us. So this is important because we are trying to scan to identify influencers. So basically, every post that is generated at by some user will basically have a label that is generated by user n, right? So the influence metric that we can use based on this model will be the probability to find a post of label I that was written by user I on the wall of someone else, which is on the wall of user n, okay? So if I know all the QINs, then I can take the sum of them and average them over all the users on the network, and I will have the mean influence on the network, right? This is my mean influence on some other users on the network. That's why I take n-1. I can also support other types of metrics, like, for example, finding at least one like post on a wall. So this at least one will be 1 minus not finding any on the wall. So not finding any will be 1 minus QIN to the power of k, because I have k entries on the list of the wall.
The metric takes into account the original post or the retweets of the...
It takes into account the original post.
It's exclusively on the original post.
Exactly. That's why I said that I mark the original post by an I, by a label, and then I keep this label throughout its... The
temporal dimension of this, the spreading of this information is not taken into account in this?
This is a steady state. That means that the mean probability, so if the system reaches steady state, so I can observe, for example, the evolution of the walls of different users, and I take the average over all these changes, and I have this mean probability to find something. Is it? So it's a mean influence, basically. Okay. Okay, so this is a very important thing to say, that basically this model allows for cloning. And this was one of the biggest problems that we had at the beginning of the modelization, how to introduce a model that allowed cloning of posts and have the Markovian property. And essentially, it took us quite some time. And by taking the structure itself of Facebook and Twitter to put it on the model, we had this opportunity to have multiple clones, because, as we have said, a post with some ID will come on the wall because it's posted at this wall. And then simultaneously, it will appear on the news feeds of I and J. And then with some rate, with some probability, let's say, it can be reposted on the wall of someone else. So this can generate basically clones of this post. At the beginning, we had started a work with Celine. And it didn't work out because essentially the first idea we had was to do it as a Jackson network. But the problem of the Jackson network would be that like if you see every post as a packet, then this post should be removed from one list, let's say, and it should one post should go only to one receiver. So because with some probability, you just choose one of your followers and you send it to him. So the Jackson approach would not work in this case because of the lack of cloning. So in order to do a mathematical analysis of this complicated model, we are going to do some modeling assumptions that will allow us basically to solve it. Okay? So the Poisson process of post and repost is something very standard. Now we have chosen one selection, one eviction policy that is suitable, okay? That's convenient. The one is the random selection from the newsfeed. That means that the user goes to his newsfeed, checks all the posts, and uniformly randomly selects one post to repost, okay? And the random eviction is something that is not very realistic, but it will work out for now, and we will see also in the simulations that it is not such a big deal. The random eviction means that once something comes in the newsfeed or in the wall, a randomly selected element is removed. So these assumptions have resulted in a Markovian model, because every interarrival time is exponential, and every choice of which object to select is probabilistic. Okay? So it's a very complicated model, but it's a Markovian model. So what is the states? What are the states? Since we are treating lists, and since we are interested in the origin of the post, it's sufficient for us to ignore, and because we do the random selection, it's sufficient for us to ignore the ordering of postings on the list. We just need the number of how many, for example, posts from user I find themselves on user J. Okay, so and this is the number of posts with origin I on newsfeed n on time t. It's 6i, and the number of posts with origin I on wall n on time t is y of I. So and this evolves, right? The steady state of these probabilities will be m times the probability of influence, ym, because m are the slots of the list, okay? And k times qi are the probabilities, are the steady state solutions, let's say, of the values y1 to yn. So this number of states is enormous, and the state of, and this is important, the state of the user's newsfeed and wall are coupled with the state of the other users. So let's understand a bit the coupling of the states, okay? So I have I'm on the newsfeed of user n, and how will this newsfeed change, okay? It will change because some other user, that is like leading user n, will either post something, or he will go to his own newsfeed, and given the specific state of this newsfeed, will make a random choice among these posts at time t, and will bring to the newsfeed of n some post. However, if at this specific time there are only posts of a specific one user on the newsfeed of user or of the leader user, then only this type of post can move. Okay, so there is a specific coupling of states, and this we do not like at all because this complicates a lot the analysis. So we have done an approximation, but the approximation is basically very elegant in a sense because it does not really change a lot the problem. So what is the approximation? Instead of saying that there are evolution of the leader, that the two states are coupled, the state of the newsfeed I and the state of the newsfeed J are coupled, instead I say, okay, if I'm interested in the newsfeed of user n, then all its leaders, we assume that they are in steady state, okay? Because we're in steady state that we're interested in. So basically, if we assume that they are in steady state, then let's see how it evolves the newsfeed of user n. There is x1, x2, xi, xj, xn are the number of posts actually at the newsfeed of user n. And so it will go +1, but if it goes +1, then 1 should be removed. So there should be a -1 in order to have always the same number in the list, right? So if we increase on the newsfeed of user n a post of label I, this can happen because either there was a posting on the wall of user I in case I is a leader of n. So if I is a leader of n, he posts on his wall, this appears on the newsfeed of n. Plus the sum over all the leaders that are going to their newsfeeds, they are searching and they are pulling an object of label I. But this now is done with a fixed probability because it's the steady state probability that is unknown, right? And what is it evicted? It is evicted from all m entries, with proportional probability, it is evicted j because of the random eviction policy. Okay? So the wall will evolve on the same way. In the wall of user n, so it will only change if the user goes to his newsfeed and finds object of I and pulls it, or if n is I, and in this case, he publishes something, okay? Quite complex. But, so as a very first result, this problem essentially could be resolved because we can have a fixed point problem where the probability to find, the steady-state probability to find posts of user I on the newsfeed of n is a sum over all the steady-state probabilities of the xi of n over m. It's just an expectation, right? So probability times event. But these will depend on the transition rates, and hence they will depend on the steady states that we had introduced, which were basically the pi's. So it's a fixed point solution because the left part and the right part, the left part is defined by the right part. So and the pi's are everywhere. Okay. However, it's difficult still to solve it, so we did a state aggregation, exactly like in like Jackson networks. So we considered basically only posts from user I and all posts that are not from user I. So in this sense, since we have always m entries on the newsfeed and k entries on the wall, the sum of them will be m and k. So basically, by defining xi n from 0 to m, we can describe all the states of this newsfeed and of this wall, okay? If xi equals to 1, that means that there is one post from I and all the rest not from I. So what do we do with this aggregation? This aggregation allows us to solve 2n one-dimensional Markov chains. And they have a bit of a difficult structure, okay? But we can do that. And then we would do again a steady state. The steady state will be written in a similar way, so we would have the fixed point problem again. But still, we can move forward because basically these can be solved exactly. Okay? So we arrived after exact solution to balance equations, and this is only through the approximation that we did with the steady state. And basically this is equivalent to the Jackson network, but for social platforms. Okay? What do they say? It says that in the newsfeed, the incoming rate is equal to the outgoing rate. So it's a bit funny because maybe we should have thought of it right from the beginning. So what is the incoming rate? From all the users that are my leaders, these are searching on their newsfeed with some rates, and they are finding with probability pik an object I, and they are pushing it on their wall and hence to my newsfeed. Okay? These are newsfeed incoming rate of I, of content I. So what is the outgoing rate of content I? It's PII, the probability to find on the newsfeed content I, times the rate of going out, right? But what is the rate of going out? The rate of the egress rate is the ingress rate, because there is a stability. We cannot lose anything, and the ingress rate is the rate of activity of the leaders. So basically, these are just the balance equations for the social platform. The wall steady state is even simpler, and we see here in a very impressive way that the probability, the steady state probability to find something on the newsfeed is written as the probability, the steady state probability to find something, on the wall to find on the newsfeed. And this is impressive because basically this shows the power of social platforms in the sense that by defining what is the steady state of posts on the newsfeed, they completely define the walls of the users. Okay, another interesting theorem that we found is that there is insensitivity. The solution is insensitive on K and M. So the size of the lists does not play any role, and this is because of the probabilistic choice that we have done. And we go further, that we write this in a matrix form. So we have basically this linear system. So the PI is the vector of probabilities to find content of I on any newsfeed. And Qi is the probability to find content of I on any wall. And essentially, this is the Leontief equation. This is a Russian mathematician who defined it for economy. So basically, this system is somehow known. But what is more interesting here is that basically A is basically the matrix that has the leader, the follower graph. So basically, A is the follower graph weighted by something, and which is this something? They are just the activity rates of users. And this is the impressive thing that here you can see that this is not 1, but it's 1 times mu, and mu is the retweeting, the resharing rate. So basically, someone can basically set mu to 0 and cut off the flow of information from. So what is A? So A is basically non-negative. It's a row substochastic, meaning that the sum of all of its rows is less or equal to 1. As I said, it's a weighted version of the follower matrix. And when the follower matrix is 0, then necessarily this matrix is 0. But there are cases where J can follow L, so this would be 1. But this is 0 because mu L is 0. Hence, users that never repost from a newsfeed alter the possibilities to post for propagation. So we call this propagation matrix, just gave a name. OK, and what do we do with that? We solve it, right? So, but to solve it, we need to inverse the matrix. We will see which matrix. It calls for the spectral radius that the spectral radius is less than or equal to 1. So we want for the inversion to be strictly less than 1, which is the case when, for example, one case is when all the posting rates are positive. And a case a bit more, let's say, elegant is for every cycle in the leader graph, at least one participating user has a leader K with positive self-post rate. This is a bit of a weaker condition. And the special case of this, so we didn't even talk about reducibility, but the special case is when it's irreducible and lambda I is positive for at least one user. So the solution, which is closed form, is basically that Pi is the inverse of I minus A times Bi, and Qi, which is basically the probabilities that we're looking for, the steady-state probabilities of influence, are C times In minus A, the power of inverse, Bi plus Di. So, but computation, the inverse should be calculated only once and then applied to all expressions for labels I equals 1 to n. But since we are talking about massive matrices here, so we suggest a fixed point algorithm that basically will resolve the same problem. And we arrive at a very simple, basically iterative solution, right, for the newsfeeds. So Pi of t is equal to A times Pi of t minus 1 plus Bi. And this iteratively will converge to the steady state for all for the newsfeeds. And then we can take the wall vector Qi by the equalities, and the Psi can be derived. So this. So we should validate it, right? So what we did a discrete event simulator. We took dynamic lists of size M and K and had a variety of selection and eviction policies. Random, newest, oldest, most or less popular. So we tried different variations because we had very strict assumptions for the modelization. And we also had various arrival processes like Poisson, hyperexponential, deterministic. And we took M equal to 20, K equal to 10, and 300,000 events. So first we see a complete graph. And in this complete graph, we start increasing the number of users, and we see that influence goes down. Why does it go down? It's just because we have 1 over n. It's just because of the definition of the influence. But what is more interesting here is basically to see the influence of lambda and mu on how the lambda and mu changes the result, because rho is lambda over mu. So 0.5 means that lambda is smaller. Lambda is half, like posting is half the reposting. So we see that when there is in the complete symmetric graph with symmetric activity, when there is a lot of reposting, we have a maximum of influence because everyone is leaving some place for the posts of the others, right? So if I'm reposting a lot and I'm posting a little, so I'm open to get messages from others. Whereas this decreases as rho increases. In the symmetric case, we had that, we checked the position, which is basically that, we have the central user, the edge user, and the corner user. There's the center, the edge, and the corner. And then we took some increasing sizes of this grid. And we saw, for example, that the central user was always the most influential, and then it goes to the edge, and then it goes to the corner user. So this is something that we can expect. We did like just some validation for a ring graph with asymmetric activity and asymmetric number of users to show that basically everything is more or less okay. And now the assumption. So the Poisson assumption was surprisingly not so strict, because basically the results are almost the same for hyperexponential and deterministic. So the arrival process somehow doesn't play such an important role. However, what plays an important role was, and this is like, of course, something that we expect everyone, is the different like newsfeed curation algorithms that a platform can apply. So first of all, we see that the random selection, random eviction was reasonable in the sense that it can reasonably substitute FIFO, like because we see here that random selection, oldest eviction, new selection, random eviction, new selection, oldest eviction, all these have the same average influence. When the influence changes is when we start playing with popularity. So in our model, we were able basically to rank on the first place, the first position, the most popular or the less popular content. And then you see that this is a mean influence. The mean influence can vary a lot. And essentially, we should show something else, which was the individual users. And there are users basically that get the maximum of influence, where in others, they get no influence at all, just because we change these like curation algorithms, let's say, on the newsfeed. So this is a very critical thing, and this should be further investigated, because as we saw, the walls are a bit mapping completely what there is on the newsfeeds. And finally, there are three nice plots to see how this model can be exploited. First of all, we see what is the difference between direct and indirect influence. So in a ring graph where you are friends direct with the 3 at the left and the 3 at the right, you see that the direct influence is very strong on your direct peers, but then it goes completely zero almost on the indirect ones. But this depends a lot on the reposting. So for example, here, rho equals to 10 means that lambda is very high. It's 10 times higher than reposting. So that means that everyone is trying basically to push their own things, and they don't leave room to be influenced by anyone else. Whereas 0.1 means that reposting is 10 times higher than posting, and then you see that there is more room for influence, let's say, even to second and third hop users. Also, a very interesting result that we were a bit surprised is the result on a grid, where we're trying to find basically, based on position, who is the most influential user. And essentially here, every user has direct friends, which is up, down, left, and right, except the edge ones. And here we were thinking, okay, the most influential should be the central, and the least influential should be the edge. But this is not true, and this was like quite impressive, and you will understand also why this is not true. So basically here we see that the most influential is basically this guy right at the corner, next to the corner, but not at the corner. And essentially the reason is very simple. Since we are taking as influence the average influence towards someone else, so basically these guys are very much isolated by the influence of him. So he will have a much stronger influence on the edge users because of this edge effect than the central user will have, right? So, and finally, the last plot is about position and activity. So, okay, this edge user, we saw that he was the worst because he was on the dark here. So he had the least influence. Can we help him get more influence, right? So because of his position, he's not very favored. So what we can do is that we want to see if he starts increasing his posting activity, if he can get much better. So, and we see here that as he increases his posting activity, the corner user is basically increasing his influence to the network, but there is also a nice event coming that the central user is not influenced at all, but rather the diagonal neighbor who was the highest influencer starts going down, and after a point he loses influence in the network because basically So imagine, based on this model, imagine a bot that is actually like pumping like mail, like postings in the platform, how this bot can change completely like the influence in the network. Okay, so we introduced an original stochastic model for post-diffusion, and we solved it. The model considers social graph, user activity, OSP structure, and reposting decisions. Of course, there are some assumptions there. And we have a closed form and efficient algorithm for the solution. And we saw in evaluation plots the importance of both position and user activity, and also the fact that reposting plays the role of information val for post-diffusion. So this is, you can find this once this goes out, our work on Infocom. And thank you very much, and I'm open for questions. Questions?
The curation process, the model of the curation process was only on the eviction of messages on, because you said
yeah, exactly. Yeah, exactly.
On time,
yeah.
And the type of curation that you are modeling with this would allow every message to arrive, and then would decide which message will
be evicted. Yeah. And this is random?
Instead of, another type of curation that would be not all the message would arrive to all the nodes. To all the followers.
Basically, all the messages will arrive. It's just that you do not have any ordering. So since you don't have any ordering, you don't decide to evict the oldest one or to evict the least popular. You just evict any random that is inside, and you don't even consider their order. That means that it's not placed at the beginning so that the user will see it first. So this we have not done, at least not with this model. I think these are very important things to be considered later on. This is just a first model, basically. But I think there is a lot of things to do with this model since we arrived in a solution. Yeah.
I think that a very important part of the what we call curation.
Facebook called it this way in a paper they had, so that's why I use the same.
Is the scoring function they're using?
Yes, exactly.
To rank the post of your friends, okay, to your own
interest. Timetable, I see.
Okay, so one possible, let's say, idea would be to take a closer look on the scoring functions.
Yeah.
To better integrate it, let's say, to integrate it your own model and to give a more realistic flavor, let's say.
Exactly, yeah.
Mike, the question is the following. Can we use the model as such to detect bots?
Yeah, so this is a very interesting question because we are also thinking of ways to extend it and to find. So first of all, I think detecting bots would mean, let's say we could detect bots maybe based on the change of statistics. So imagine, for example, at the beginning, there is a normal activity, what we call normal activity, and we detect a major change of activity at some area in the network from some point on, right, from some time on. And maybe we can search based on this algorithm to see which is this big influencer that changes this equilibrium, and then maybe handpick whether this is a bot or not. This would be, for example, a way that I could imagine.
So actually the deviation from the normal behavior.
Yes, exactly.
Is the hint for detecting bots.
I believe so, because I have also read some other papers that...
if this is the only pattern, let's say, if bots becomes more and more, let's say, clever to exhibit different behavioral patterns in the social platforms.
To be honest, this is a very nice question. For the moment, you see that we see basically the social platform as a mechanism, more like a decision of each user. So the problem with this model, for the moment at least, is that it kind of unifies behavior of everyone, and it does not start, taking some users that may exhibit a different behavior than others. The only thing that we do as different would be the number of users these people have and the amount of posting and reposting. So basically, we could search this algorithm to detect cases where there is no reposting, but there is only a lot of posting, because bots are doing this. Bots are not, for now, they don't repost a lot. They just post massively, so they have a large lambda over mu ratio. so lambda was the posting and mu was the reposting. So basically, we could search for such entities in the network to see how these could change the statistics, basically, of influence. This is what my impression would be, basically. Okay.
I have several questions. The first one would be, did you try to apply your methodology on real instances of Twitter or Facebook?
We are now in the process of doing that.
Okay, and I guess that the main issue will be to estimate your lambdas and mu.
Exactly, this is very difficult.
I had a second question.
Yeah.
At the moment, you plotted C according to, if I remember well, different kind of eviction.
Right, yeah.
Yes, and so I have the feeling that when the number of
selection,
users
basically,
is large,
yeah,
you don't really care about the eviction process. And in practice,
why is that?
this platform involves a lot of users, so maybe
why is that?
No?
No,
Sorry?
I don't think so. No, I don't think so. Why is that? Why don't we care?
You are plotting sub-C according to various eviction.
Because you see this number, the 21. This is what is your question.
Yes, I guess this is the number of users.
Yeah, but I can put it to 500,000 easily. It's not a problem. The problem would be basically that since I defined it as 1 over n, then I should basically scale bring the camera focus out. It's just a focusing effect. The algorithm is not problematic up to 500,000. The algorithm is problematic basically for 6 or 7 million. We have some, like there we will have to play with sparse matrices, and it's a bit more involved. But this is just an example. We will make basically the algorithm open, and at least not the sparse version for now, and you can easily put 500,000 users there. Okay.
Yeah, and I have a last question.
Yeah.
I have the intuition that it's maybe totally wrong,
that
there are some parts of your work which are related to PageRank-like algorithms. Is it
possibly
totally wrong? Maybe.
Well, I mean, PageRank is not a Markov process, right? It's a Markov chain. So the PageRank does not have the temporal aspect. So this has a temporal aspect. It's a very different work, because what we want is that basically to show that users have different activity. One is posting 20 times more than the other, or reposting, and then the result is completely different. So I would say that of course it's a Markov chain in this sense, but we don't have basically anything from the PageRank. In a sense, we don't have anything, like you don't leave, like you're not a surfer that goes and does let's say a random walk and then suddenly decides not to and then chooses any random user. But we just show really based on the friendships how these posts are diffusing. So at the moment we don't change anything on the friendships, or maybe this is an interesting thing to bring temporal evolution on the network. Another interesting thing could be basically to use the model to predict cascades. For example, finding cascades, that are more, this is like really what we would like to do. And it's a very nice question if the model can follow.
Also a question if the computational properties of this model are better than models that have been purported for.
Yeah, exactly. To be honest, this is exactly the point, that basically the computation is a very big aspect, and now we're working on this. And this thing is that this computation is basically boils down to if it opens anyway to the inversion.
Yes.
This is where even if we have this approach, like applying this for several millions of users is a big challenge basically. So we're trying stuff. For example, you can try all the algebraic methods, and you want LU factorization, sparse, many things, and it's a problem. Yeah. Mm-hmm.
So in your simulation, most of the things are very symmetric. So what would happen?
No, it's not. Basically, please.
So what would happen if you have cliques in your graph, like a part that's more densely connected than the rest? What would happen?
The model will work, that's for sure, because, for example, this was an example where there's no symmetry. We broke every symmetry there just to see if it is valid.
This is more like random thing. What I meant is you have a graph. There's one part that's more densely connected to each other than the rest.
Yeah, I mean, I don't think that the model will not work as a model, as a mathematical model. I mean, but we should see what maybe this clique can produce in reality compared to what we expect to see from the model. I think this is the appropriate question. Like, the model will expect something, but maybe this clique, because it is a clique, behaves completely differently than what this model predicts. So maybe the clique will only post among themselves, and they will completely ignore all the rest of the users. So in this case, we might see other things, you see.
I'm asking this because, of course, you're looking at Facebook and Twitter, but then, like in the Chinese social media,
right?
What could happen is on top. First, there is like clique, as you said, they post to each other a lot, and on top of that, there is like the trending part. They look at what other things that's currently trending, like being reposted a lot. So I think that's plays with the popularity.
Right.
So then
the trending, yeah, exactly.
It influences the entire graph a lot.
Yeah. So we need to take into account these. Like one of the most important things is exactly how to incorporate this trending or most popular approach in the newsfeed. Exactly, this is extremely important because I mean we want to see basically first of all the data, because now we want to make first comparison of what we have and what the data brings out. Let's hope that at least some positive. I'm a bit optimistic, but I'm not so optimistic because I think things are working in a much more complicated way. But let's see if we have.
Challenges from the data always push theory ahead.
Yeah, exactly. Yeah. What fish do we catch? Exactly. Okay. Any other question? Okay. So, thank you very much for being here. And also, I would like to say again that this is a joint work with Bruno Benat and our stagiaire. So, he couldn't come here today because of a course. And we thank him also.